This is Anansi the spider. He's got 8 legs, a big head, and a very fat body. Anansi loves eating. Rabbit is Anansi's friend. He is cooking greens in his pot.
I can smell greens.
They are not ready yet. Why don't you stay and wait?
No, I can't stay, but I've got an idea. Pull the web when the greens are ready, and I'll come running.
Okay, Anansi.
I can smell beans.
Come and eat our beans with us. They are almost ready.
No, I can't, but I've got an idea. Pull the web when the beans are ready, and I'll come running.
Okay, Anansi.
I can smell sweet potatoes with honey.
Yes, that's right. Come and eat my food with me.
No, I can't, but I've got an idea. Pull the web when the sweet potatoes are ready, and I'll come running.
Okay, Anansi.
When Anansi arrives at the river, all his 8 legs are tied with webs. All the food is ready, and the animals pull the webs. Anansi falls over, and his legs get thinner and thinner.
Maybe that wasn't a good idea after all. Look at my thin legs. Oh well, maybe there's some food at home.
Now we're going to start into our next category, which covers a lot. So I can appreciate that what I'm showing you here may be a little bit clouded by that light. So I'm going to read it. It says grade 8 linear equations, relations, functions, etc. So we're going to try to, well, we're not going to try. We're going to begin to discuss all of these issues and all of the concepts, and in the process I'm going to tie it together for you, so as we go forward you'll have kind of like a road map to follow. Now the way we're doing this, we've done for the past 3 or 4 years, so all the 8th graders have been able to grasp what we're talking about now. So there's no reason to think for 1 second that you won't do the same thing, because it's really not so hard. Now we're going to explain what we've been talking about up to now and why we need it. So I've mentioned last time, I believe, that linear means a straight line, like this is a wavy line. So it's not a linear equation. There's no linear equation that would describe this red-pink line. So a straight line, a linear, would be like so, A, B. We'll put our marks that show that it's a line and not a line segment. So AB will go on to infinity in this direction and infinity into this direction. Now that particular line would have a standard way of describing it, and it will be described by this equation, y equals mx plus b. This is what you have to get into your mind right now. So you'll write it down when you go back over this. So this is the standard form for a linear equation. Now I'm going to explain all of this And if you remember, when we mentioned it previously, the letter M here tells you what the slope is of this line. And I don't want to confuse you right now, but you'll understand this as we go through examples. But if we use the substitution principle, I won't even start that now. So let's first talk about what we're doing here. So here's an example of what we mean. You know what this is. That's your coordinate plane. You have the origin. You have the y-axis, the x-axis. You have your negative numbers here, your positive numbers here, your positive here, negative here. So you have quadrant 1. All points in quadrant 1 are positive, positive. As you know, they are ordered pairs. So that means x comes first, then y. In quadrant 2, you know that you have ordered pairs, and the ordered pairs are negative and positive. Everything in this quadrant is negative for x, positive for y. You got quadrant 3. And it's ordered pairs again. And everything in quadrant 3 is negative for x and negative for y. Minus, 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 plus, 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 and plus, minus. So quadrant 4. This is all review. Ordered pairs, x, y, and they're all plus, minus. So if I give you a set of coordinates, for example, e.g., for example, if I say I have this coordinate minus 8, 11, and ask you, where is that? You know it has to be negative for x, which is coming to the left, positive for y, so it's in quadrant 2. You say that's in quadrant 2 because it's negative, positive, and everything in quadrant 2 is negative, positive. Every point on the y-axis has a coordinate that's 0 for x and something for y. It could be positive for y, meaning it's above 0. If it's negative for y, so I'm going to say it could be plus or minus. If it's plus, it's above 0. If it's minus, it's below 0. Every point on the x-axis is going to be something for x and 0 for y. So likewise, it could be plus or minus for x. If it's minus for x, you know it's on the left side of 0. If it's positive for x, it's on the right side of 0. Now, any point that's on the line, so I'm going to draw two hypothetical lines, just so you see exactly what we're talking about. So let's say a line goes like this. There's my line. I'll put arrows on it, and you know what that means. It goes on forever in both directions. Now, here's another hypothetical line going like this. I'll put my arrows. So I have the red line and the blue line. Just like the rapid transits have a red line and a blue line. You might have a green line too. So you have a red line, a blue line. I'm only putting these here right now to explain one thing about this letter M. I say the M tells you what the slope is. The slope, now you have to write this down and get it into your minds because that's going to be important. Slope is I'm going to use a word now that might be troubling, but you'll get it straight, is the trajectory and we'll talk about this, so don't worry about it. It's just a new word. It's the trajectory of the line as it moves from left to right. It sounds complicated, maybe, but it really isn't. So here's what it's saying. As this pink line goes from left to right, it tends to go down. So its trajectory is a downward motion as it goes left to right. By comparison, the blue line, as it goes from left to right, it goes up. It keeps going up, up, up. So one line is going up and one line is going down. So any line that goes up as it goes from left to right has a positive slope. So I'm going to put M, I'll put them both in green. M is positive because that line is going up. Here M is negative because the line is going down. So this is important. You'll see as soon as I show you another example. So as the line goes from left to right, if it's going upwards, the slope is positive. If it's going down, the slope is negative. And the point where the lines cross these axes, like here and here, those are the intercepts. So the y-intercept is where it crosses the y-axis. The x-intercept is where it crosses the x-axis. So I'm going to write those words right there so you will have it. So this is the y-intercept, I-N-T-E-R-C-E-P-T. I'm writing it small, but you can get it. So the y-intercept, I-N-T-E-R-C-E-P-T, is where this red line crosses the y-axis. The x-intercept, which is right here, x-intercept, I-N-T-E-R-C-E-P-T, is where the pink line crosses the x-axis. Now the coordinate here we know is 0 for y, right? It didn't go up and it didn't go down, and it's some value for x, and it's positive. So it's positive x, y. So where the line crosses the x-axis, the value of y is 0. Where the line crosses the y-axis, the value of x is 0. So it's x and it's something positive for y right here. This may seem confusing, but if you keep going back over it and you look at the drawing, you'll see. So this value is 0 for x because it didn't go right and it didn't go left. It's on the axis. So everything on the axis, on the y-axis, has a 0 value of x. So that's 0 plus something for y. This point, you should now be able to see yourself. I'll put it in black. So this is the x-intercept for the blue line. So x-intercept, I-N-T-E-R-C-E-P-T, T-E-R-C-E-P-T. So the value here is going to be 0 for y. It's not up and it's not down. And it's some negative value for x because it's on the left side. This intercept is the y-intercept for the blue line. C-E-P-T. And the coordinate at that point, the value is going to be 0 for x because it didn't go right and it didn't go left, and something positive for y. So now you might ask, why do we care about this? Well, we care about it, and you'll see this as soon as we do a little actual work. We care because if we can figure out where 2 points cross the axis, we can easily draw the line because it only takes me 2 points to make a line. Once I have 2 points, I can draw a line. Once I have this point, that point, I could draw the line. So it takes 2 points to make a line. And here's a key concept that I want you to pay close attention to now. This point right here where these two lines cross, we call the intersection. I-N-T-E-R-S-E-C-T-I-O-N, intersection. Just like the street. When you get to the end of one street, it crosses another street, and we call it an intersection. So the intersection is where two lines cross. Two lines can only have 1 point in common. They can only have 1 point of intersection. Because if they have 2 points in common, they'd have to be the same line, because two lines can only cross in one place unless they're the same line. So when you're asked to solve two linear equations, what that means is to find the 1 point that they have in common. I'm going to show you how to do that, so it's not going to be difficult to do at all. So you'll see that these things, once you get a few concepts, you can do them pretty effectively. So the intersection of the two lines is the solution. Intersection of two lines is the solution. Now, right now, all I need you to do is to make sure you write these things down, you listen, you play them over so that you have them straight in your mind, because these are the key concepts to do the problems. So I'm going to show you what we mean too. So I'm going to clean this off. You'll go back and you'll look at it, stop the tape, make your own drawings, write down the things, see if you can understand what I'm explaining. You see them here, so you can see if you can reconstruct it and you know that you understand it. So now we're going to go to this and do some examples. So I'm going to pause the tape, clean this off, and we will do some more thorough analysis of what we're talking about now. Okay, we're going to come back, and maybe we'll just do this part and stop for right now, and I can keep going and make you another one tomorrow. Now I want to talk about quickly introducing relations and functions. They seem to be hard for a lot of people to understand, but it's really not so complicated. The first thing I want to help you to understand is a relation is a set of ordered pairs, like we have here. This is a set of ordered pairs for this equation that we did before. This is a set of ordered pairs for this equation, and this was a set of ordered pairs for that equation. So a relation is a set of ordered pairs. A set, that ink is not good, a set of ordered, O-R-D-E-R-E-D, ordered pairs. That's a relation. So all three of these are relations. This is a set of ordered pairs, a set of ordered pairs, a set of ordered pairs. So you say, well, Dr. Whitaker, what's the difference between a function and a relation? Well, a function is a set of ordered pairs, is a set of ordered pairs, Now here's the difference. It's a set of ordered pairs where every x has only one y. Now that will sound a little tricky to you, but once we do a couple of examples, it won't be that difficult. So I have another drawing to show you this. Every relation or every function is a relation, but not every relation is a function. That may sound confusing too. So let me put it like this. Every cell phone, every cell is electric, is electronic. Every cell phone is electronic. But not every electronic thing is a cell phone. There are other electronic things that are not cell phones. But every cell phone is electric, is electronic. So a function, every function is a relation, but there are some relations that are not functions. So once you gather that, once you make that distinction, it'll be very easy for you to get it. And it usually comes across to a lot of students as difficult. But just imagine every cell phone is an electronic device, but not every electronic device is a cell phone. You could have a toy that's electronic, but it's not a cell phone. You could have a TV that's electronic, and it's not a cell phone. But every cell phone is electronic. But there's a whole universe of electronic things that are not cell phones. So every function is a relation. But see, there's lots of relations that are not functions. Functions is a part of relations, but relations can exist and not be functions. So now I'm going to show you some pictures of it based on the definition. So a relation is a set of ordered pairs. Okay. Here's a set of ordered pairs. Set of ordered pairs, set of ordered pairs, set of ordered pairs. A function is a set of ordered pairs where every x has only one y. So let's say we'll take the examples we have. Right now they are relations and functions. They're a set of ordered pairs which makes all three of ours a relation. And they're also functions because they only have, every x only has one y. So how could I demonstrate to you what is the difference? Let's say we had this set of ordered pairs and we had -2 was another coordinate. And we had this set of ordered pairs and we had -1 and -7. And let's say we squeezed in one more here. We had 0, 6. Okay. So now we say these are relations because they're a set of ordered pairs, relation, relation, relation. But they're not functions anymore because here 1x has two different y's, 0, 8, 0, 6. So you got 0 and it has 8 and 6. So a function, every x only has one y. This x has two y's. One's 8 and one's 6. So that says this is not a function. Not, I wrote the n funny. So this is not a function because the x value of 0 has two y's connected or associated with it. One is 8 and one's 6. So that eliminates it. But it's still a relation. So that equation would now be out into this area because it's a relation, but it's not a function. Same thing would be true here. This is no longer a function, not function. And you can see why. Because the value of -1 for x has two different y's. One is -1, the other is -7. So that eliminates it as a function. Same thing here. I've made it easy to see. So -2 for x now has two different numbers. So this is not a function anymore. So every function is a relation. As you can see here, every function is inside the big relation circle. But every relation is not necessarily a function. Now, I hope that clears that up a little bit. Now I want to show you a visual image of what we're talking about. Because once you see the image, you'll see what I mean in a different way. So I'm going to clean this off. We got 8 minutes, so maybe 2 more minutes and we'll stop, and maybe this will be the total lesson for today. So I'm going to clean all of this off and show you some examples. So we're going to make a coordinate plane as soon as this dries, so my marker will go very nice. And we're just going to look at some examples. And if you can get this, we'll be way ahead. And if we can't get it, we'll come back to it. So either way, it's no problem. So let's say we have this coordinate plane that we're working with. So if I make this line and ask you about the slope, you would say, well, the slope is negative. I don't know exactly what it is, but I know it's negative. And I say, well, how do you know that? You say, because the line is going down as it goes from left to right. So the slope has to be negative. And so I would say, well, compare that to this line and tell me what you think. Is that a linear equation? You say no. I said, how do you know that? You say, because this is not a straight line. Linear equation means it's a straight line. Like this is a straight line. The pink one is a straight line. This is a curved line. I'll say, well, could this be a relation? You say, yes. I said, how do you know that? You said, because a relation is a set of ordered pairs. And it takes a set of ordered pairs to plot all these points. So it is a relation. I say, is it a function? You say, no. I say, well, how do you know it's not a function? Why do you say it's not a function? And you say, well, if I took a piece of paper and imagine, for example, I put a little line here and the value of x is 1, 2, 3, 4. I can see that x is 4 anywhere on this line, but here's a coordinate. This will be 4 something for y, and this will be 4 and something different for y. So I'd have this x of 4 would have 2 y's. So would this one. So would this one. So would this one. So a function says you have a set of ordered pairs where each x has only one y. So if I see a shape like this, I know that can't be a function. It's a relation, but not a function. This one is a relation and a function because every x only has one y. So I would say, well, okay, smarty pants, let's see what you think about this. What if you had this diagram? I say, is that a relation? You say, yes. How do you know that? Well, because it's a set of ordered pairs that are making that configuration. I say, is it a linear equation? You say, no. I say, well, what makes you say that? Because a linear means straight line, and this is a curved line. So it can't be a linear equation. I said, could it be a function? You say, yes. I said, what makes you think that? You say, well, even though it's not a linear equation, meaning it is a relation, it's also a function because there's no point at which one single x has 2 different y's. So that would qualify this as a relation and a function, but not a linear equation. So I'll say, well, what about one more thing? Let's just see. Take this one more step and see if we really know what we're talking about. I say, well, what would you say about this same thing, which is now horizontal? What if that same thing was going like this? So I would say, is that a linear equation? You say, no. I say, what makes you say that? You say, well, linear equation means a straight line, and this is a curving line. It's not straight. So it can't be a linear equation. I say, is it a relation? You say, yes. What makes you say that? Because it takes a set of ordered pairs to make this plot all these points that I can join together to get this shape. I say, is it a function? You say, no. I say, what makes you say that? Well, a function, unlike this horizontal wavy line, every x had only one y. But if you do that same thing vertically, so it's standing up and down, then I can see all these points where one x has 2 y's. It has this y and that y. And it has a third y. So all these are x's negative 1, 2, 3, let's say. X is negative 3. And look, it's got this y, this y, this y, this y, this y, this y. So it doesn't qualify as a function. So it's a relation. It's not a linear equation. And it's not a function. Because there's one x right there, negative 3. That from the looks of it has 1, 2, 3, 4, 5, 6 different values of y. So that eliminates it for meeting the definition of a function. So let's stop there. We've talked about linear equation a little bit, the distinction between relation and function, and we'll come back the next time and we'd have to talk about how to find the slope if you didn't have the formula. Because there's a method to do that. You won't always have the linear equation. You'll be looking for what the linear equation is. Just like this pink line. I didn't give you the linear equation, but we do know something about the points. If we had a really good graph, we know this intercept right here is 0 something, and this is x0. So we could find the equation working backwards. So that's what we want to do the next time. But if you do some practice, you're going to see, you'll have questions of distinguishing between relations and functions, plotting linear equations, which you're just going to make your boxes and determine your ordered pairs. You only need 2, but I would say always get a third one just to double check. Because if the third point is on the line, you know it's conclusive proof. But if you do it the way we did it, you'll find the lines nonetheless. So that's enough for today. Study hard, make your notes, go back and review the tapes, because you can get it and you always have the video to review it for you. It just as if I was right there, we were talking about it all over again. So be good, be safe, and be happy. Bye-bye.